So in this video we're just going to do another example of KCL. Depending on how long it takes to go through this example, we might put another example in this video as well. If not, we'll just make another video. So what we got going here is we have a circuit here, which again you might want to pause to redraw the circuit. And we've got V1, V2, and I1 that we're supposed to find, and they're all labeled in the circuit here. So this is what we're given. First off, let's try and not make silly mistakes. Sometimes people want to say, oh, well, I can figure out I1 just using current division. But remember, we need something that's purely parallel, and this circuit's not purely parallel. Plus, I've got two current sources going on, and there's a lot more going on here. So don't make the temptation of trying to do something as simple as current division. So make sure to be aware of that. Now, what we're going to do here, what I always like to do is, again, identify the nodes that I have present here. So I've got a node right here, a node right here, and a node right there. There's three nodes in this circuit. And that also, when you're just given a random circuit, eventually you're going to have to be able to determine whether I should use nodal analysis or what we're going to discuss in the future, something called mesh analysis. And often you want to do it based off of like, well, how many loops would I have or how many nodes do I have? And since I only have three nodes, this would be a good kind of like, oh, well, nodal analysis would make sense to find my unknowns. Because remember, we always can find one node because we always have to label a ground somewhere. And again, the most place that makes sense here is on this bottom branch here, is to make this ground, which again means this is 0 volts. And that makes sense because then V1, in fact, I'm just going to go ahead, instead of labeling this node A, I'm just going to label this node, because you know I like to usually use letters. I'm going to label this 1, and I'm going to label this node 2, because if I look at the voltage here, that's absolutely going to be V1, because again, if I go from this positive side, the V1 being the drop across the 60 ohm, it's this voltage dropped over this voltage here, or I'm sorry, this voltage minus this voltage, and since it's 0 at the bottom, it's just this top voltage. So this node voltage here, we've labeled them, but that would be V1 voltage, and this voltage here similarly would be V2. All right, so now we just need to write our node equations. Now, I'm not going to go ahead and do the same writing out all the currents. We're going to kind of do it in a little bit quicker way here. So I'm going to just say node 1, because that's, we want to find V1, so that makes sense to do node 1. And then if I do that here, well, first off, I've got 15 amps coming into the node. And remember, when we do resistors, we always do the current leaving the node. So it's the voltage at that node minus the voltage at the other node divided by the resistance. And I'm going to go ahead and say, well, I'll go ahead and write this would be V1 minus 0 over 60. And then I'd also have V1 minus 0 over 15. So that's the current through the 15 ohm. So the first one's current through 60 ohm, then current through 15 ohm. Now I've got to get the current through the 5 ohm, which actually is also I1. Now you could write I1, but I want to try and get as few variables as possible. So I'm going to do plus V1 minus the voltage would be V2 over 5. Now, we run into a problem right here with this problem, is that I've got an equation now with two unknowns in it. It's not the end of the world, it just means I'm going to have to write another equation down. Now, before I do that, let's go ahead and do some algebraic manipulation on this to clean this equation up. And what I mean by clean it up, let's get rid of the fractions. I always find it useful to get rid of the fractions. So I'm going to multiply through by 60. So first off, 60 times 15, let me pull out my calculator to make sure I do that arithmetic correctly, is 900. So you'd have 900 is equal to, well, 60 divided by 60 is 1, so you get V1. 60 divided by 15 is 4, so you get 4V1. And 60 divided by 5 is 12, and so you'd get plus 12 times V1 minus V2. Now cleaning it up a tiny bit more, combining like terms, you get 5 plus 4's, I'm sorry, 1 plus 4 is 5, plus 12, so we'd have 17v1 minus 12v2. So this is, I'm going to just label it equation 1. So it's still a simple equation, but I got two unknowns. Well, since the node I wrote was at node 1, finding voltage 1, the next equation I probably would want to write would be at node 2 because that's where voltage 2 is. That's where my other unknown is. So let's go ahead and do that. So node 2 well, let's go back up here. Now remember, I'll go ahead and draw them in blue. We're going to draw all the currents through the resistors as leaving. That's our notation we do when we do KCL. It just makes the equations easier for the resistors. And also notice this 5 amps is leaving the node. So I would have 0 is equal to 5 amps is leaving plus, well, the current through that 2 ohm would be V2 minus 0 divided by 2. And then the current through the 5 ohm, now again, I'm drawing it leaving the node, so it's going to the left, and that would be V2 minus V1 over 5. So this would be plus V2 minus V1 over 5. And that's again equal to 0. So just like before, let's clean this equation up. But right now we should see this equation also has two unknowns, but it's got the same two unknowns as my first equation. So if I clean this equation up, I'll just have a system of two equations and two unknowns. So if I multiply this by 10, of course 10 times 0 is still 0, so I get 0 is equal to 50 plus 5v2 plus 2v2 minus 2v1. That's just multiplying everything through. And then again, kind of cleaning things up, my equation would be minus 50 is equal to, and I like to make sure to write it in the same order, minus 2v1 plus 7v2. So this is my second equation here. So I'm going to go ahead and write them again here. I'm going to write 17v1 minus 12v2 is equal to 900. And then I have minus 2v1 plus 7v2 is negative 50. And then we solve the system of equations. Now, any algebraic technique you use to solve the system of equations is valid. Personally, I would use a calculator that has a matrix, and I'd write an augmented matrix of 17 minus 12, 900, minus 2, 17, negative 50, and then use the command in my calculator to do reduced row echelon form. And if we do that, we get the following. 1, 0, 60, 0, 1, 10. And then that means, because if you think about what this is, this column is representing V1, this column is representing V2, and this is the kind of, I'll just label it as B, like it's equal to some number. But then now here I've got V1 and V2, the columns still represent the same thing, so I have V1 is equal to 60 volts, V2 is equal to 10 volts. So I've actually gotten 2/3 of the problem answered, because if I scroll back up, it was asking me to find V1 and V2. So I have found V1 and V2, so those are 60 volts and 10 volts. Now the only other thing I'm asked to find is I1, which is the current going through the 5 ohm resistor, but you need to notice the direction here. I know I emphasized it here, made this really ugly arrow, but what that means is we need to get this arrow here, that I1, we would do it as V1, you basically always do it as where the arrow is originating. It's originating at the V1 node, and it's going to the V2 node divided by 5. And so to get I1 then, it would be 60 minus 10 over 5, which gets me 10 amps. And so we found everything that the question asked me to. And this video is about 10 minutes right now, and the next example I want to do, which is going to be the last example related to nodal analysis, is going to probably be 10 or 15 minutes, so I'm not going to put it in this video, and I'll put it in the next video.